everybody. So, we have just finished the first part of the tutorial, which means we have set up a basic volume rendering engine. It's experimenting, we didn't get to this part yet. Here, I'll take this down. So we got about this far. There we go. So we got about this far, right? Basic volumes and stuff. So now we are going to actually shade this. So I am going to start by mentioning what this is going to make you, what you need to know for this. All right. So this is very math heavy. You have to have some concept of, you have to know the concepts of integration and differentiation and calculus. If you want to understand the first part. If not, or if you don't have that, then these equations will be meaningless to you. And it's just going to be practice of implementing equations in Blender, which, I mean, it's sort of useful, but you're not going to get the full extent of this tutorial if you don't know calculus. So we need to work on light transport functions, and that is fun, isn't it? So this is fun. So what we need to do right now is we need to find basically we need to find how much light propagates through a volume at if we go a certain distance through a volume. So for each, now we discussed in the last time, basic volume emission is just that it's basic, right? It adds up over time, right? So volume scattering is a bit more complex. So we have a certain budget of light, we can imagine it, and we're scattering some of that away as soon as we get into the atmosphere, and we're scattering some of that away as soon as we leave the atmosphere. We aren't going to deal with light directions right now. We're going to assume the light is just constant throughout the scene, and then that will be what we do next time, and that's a bit more fancy math. But right now we're just going to have basic constant light, and we're going to deal with that later, and we're going to just figure out what color our basic volume is under the most basic of light conditions. So how do we model this sort of exchange of light between emission and what's carried? So we can model this by an exponential function, right? And we can figure out that because we know how much light reaches a certain distance away from the camera if our volume is constant. And that's modeled by an exponential function. We're going to do e to the negative x, and that's basically as basic as it comes. But we don't want as basic as it comes because this isn't accurate. So what we need to do is we need to add a coefficient for the density. I'm going to use f. Boom. But even this isn't enough because the scattering is proportional to the density. If we have more density, more light's going to get scattered, right? So f goes up here. We get this. And then we have certain color bands, and we're going to model this by using A, B, and C. So let's add a slider for A, and then let's duplicate this. Oh, wrong one. I was practicing this on another Desmos. You can see some of the functions we're going to create here. I'm going to delete these. I'm going to see if we can. I guess we can't really control the color. Maybe we can. Let's see if we can get red, green, and blue. There we go. Alright, so we're going to add one variable A, that's going to be the red band, another variable B. We're going to do, so each of these are their own independent scattering equation. and then we're also going to do C for the blue band. So each of those is their own independent scattering equation, right? So we treat them independently, and each of them is like, that means they're also their own density, but there's a master density, right? So as more blue light gets scattered away, and let's say we have a bluish tint, right? So let's do something like, there's very little red, right? There we go. Disregard what's happening over here, only look at what's past blue. So we can see, oh, there we go. So we can see this sort of being modeled, and we can look at this in the atmosphere, right? We have this, this x-axis represents how far out we're going in the atmosphere. This is how much light reaches that point from our camera, or how much light we are seeing from our, how much light that's being emitted at that point are we seeing. So we see if we're very close to the camera, we're seeing blue light. But as we get farther, we see like more yellowish, and then you can see the red channel is at the top, and then blue channel is way down there, so very little blue light. It's a pretty simple equation, right? Now let's throw absorption into there. Now absorption is fun. So let's just isolate absorption for a second. So absorption looks like this. If we have, we're gonna have, let's actually, you know what, let's call these R, G, and B. And then, just to make that a little bit easier. All right, there we go. So we're gonna have R2, G2. These are gonna be our absorption color channels, and C2, or sorry, B2. And then our absorption master coefficient, which is going to be F2. So let's hide these. Let's just isolate these. So we have, this is actually sort of simpler, sort of not. So this is again an exponential function, and we're going to do e to the negative 1 minus R2 x. You can see that this might not make a whole lot of sense, but we're just assuming the light that this is absorption is complete white light, and this is how much light's being made to, this is how much light is making it to the area. Now let's duplicate these for our different functions. Let's see if we can, there we go. Oh look. Let's see if we can get a blue one. Nice. 1 minus G2. 1 minus B2. So this gives us our desired behavior, because, and it's not very intuitive at first, but when we see what this does, you'll quickly understand. So if we're absorbing only, if our absorption color is blue, look at what happens. If we aren't absorbing any blue light's the only thing that makes it there. If we're absorbing no light at all, meaning these absorption things are at 1, I mean we aren't absorbing anything. But we are absorbing, if we're absorbing red and green light, we can see we're left with a lot of red light. Right? Pretty simple, to be entirely honest. And we have to add our master coefficient there, so let's add an F2. And just for convenience, let's multiply this by our regular atmosphere scattering master coefficient. So that's F. You can see this scales it down on the x-axis basically, right? So as you can see, more light is absorbed. There's less light that makes it to the camera. The farther out we are, if our and that amount goes down even further if our master coefficient here gets higher, if our density gets higher, right? Pretty nifty, eh? So how do we model this? So if we are absorbing this much light in addition to what we're absorbing from scattering, well, we kind of have to multiply these by their respective scattering counterparts. So there we go. And let's add this into the equation for each one of those. And let's so this is a bit interesting, isn't it? So let's change our master coefficient here down. We can see if it's 0. Basically just get our atmosphere thing. I'm going to change this to 1. So now what we have to do is we have to actually we're only modeling how much light makes it, how much light we're seeing from a certain point here, and that's what this is. What we really need to do is we need to take the integral of this to find the area. Now, for those of you that have done calculus, this is easy. It's a simple exponential function. For those of you that haven't, well, welcome to calculus, eh? So let's start by converting these into one exponential function. That way we aren't doing any integration by parts. So we take this negative FRX and we just add this. And then we take this. You see the same thing. Let's do that. I'm, by the way, just going to do this for the red, and then we can copy this over. So now we have a very simple function because all of this is just a constant. Now I'm going to pull this f out and then distribute. I'm going to pull the negative f out and then distribute. So we are going to have plus. This is just going to make it a bit easier on ourselves. What do we just do? What happened? So we pull the f out, pull negative f out. Oh, we need to pull the x out as well. There we go. All right, my bad there. That got me confused for a second. So there we go. Now we need to integrate. So this is our, this is the, if we use u substitution, this is the u right here, right? So we basically just We're going to copy this, and then we're going to divide the function by it. And then since we needed to use a definite integral and we are integrating from 0 to x, we need to do -1 plus, I think. No. Sorry. So this, we need to do, so FR is our, we need to put the -1 plus after the FR. Sorry, minus. And then change this to negative, I think. No. Alright, that's how we do it. My bad. So the FR is positive, and then we need -1 plus this. Or if you want, let's this is simpler to understand. There we go. That's our function, and we can pull out the f, or actually the negative f. And then we see basically what happens is this is our function for if we go a certain distance, this is how much light we are seeing just from everything until that. And this is going to be very useful. So let's copy this to the others, eh? And then, oh, come on. Control C. Control V. Now we are going to replace R with G, this one, because R is irrelevant because this is the green channel. And R2 with G2. I think that's it. I hope I didn't muddle something up. And then do the same thing. Huh. What did I do? I did something wrong. Okay, so we have this. We're going to add this. There we go. All good. Now let's pull F out. There we go. So let's pull Fx out. Sorry, negative F out. So that should be good. All right, let's save this so that we know what it looks like. Okay. just to double check ourselves. Pull negative FR out, or negative FX out. What's going on here? Why is this not working? There we go. Okay. Now we integrate this using the process below. And divide this by the coefficient. Right, that should theoretically be correct. There we go. And then we R times 1 minus that. Oh, never mind. Not this, we need this minus 1. There we go. And if we do good. All right, sorry for that trip up. Let's figure this out for the rest of them. And let's see if we can observe the appropriate behavior. All right. All right. Awesome. There we go. So this might not look especially intuitive right now, but if we have, but when we implement this, you'll see what it looks like. So let's see actually how we're doing on time. 23 minutes. I think we can do that. Yeah, I think this will be fine. I think let's implement this, and from there we will. Yeah, so in the next episode we'll deal with lighting and actually iterating this, and that'll be next one. So let's implement this real quick. So we have our equations here. So we want to have an atmosphere color, and by the way, I already made an atmosphere color thing. This is just an RGB. I put in a node group so that we can access this other ways. That serve as a sort of buffer, I guess. So let's implement this, hey? So we need to basically create, so we need to get our R value, so we're going to separate RGB. This is our R value for that. And then we need to get the density, or not the density, alright, so let's create a value that is atmosphere density. Let's put this in a node group. This will be atmosphere density. And that'll actually be what you plug in here, and I'm going to set this like a 101. So then we multiply that by the distance we have to go, which we have done right here. And then we do what's in these parentheses, so we are multiplying that by our red value. Plus the absorption amount, which will be we're going to add another value. This will be absorption amount. And we're, by the way, we're going to need another RGB, and this will be our absorption color. There we go. So R plus F2, and then we're going to multiply this by 1 minus the R value of this, so the red channel of this. And that's what we're multiplying that by, and that is what we are multiplying this by. And then we are raising e to the power of this. And oh, I forgot, we are multiplying this by -1. There we go. Alright, so we got the top half of that, or actually almost, because we have to subtract 1 from this. And then multiply this by R, which would be this. And then we just need to divide it by the what's inside that those parentheses right here. Right here, which we have where is that? Which we have right here, so we're going to divide by this. Alright, so I'm going to grab all of these and I'm going to move this over. Now we need to do this for each channel. So we got our reds. Now let's get our greens. I'm just going to duplicate this entire thing because, I mean, we can. You don't really need to, but I mean. So plug green into there. Then duplicate this again. This time we're going to do it with the blue. Alright, now let's use a combine XYZ or combine RGB. And plug these each into their respective colors. And let's see how this looks, eh? 0% chance it works. Is it not working? Of course it isn't. So I'm going to multiply this by 0 to see if this is the issue. Alright, so this is a good demonstration of what we can do for the troubleshooting method. Alright, let's see what we can do here. So it looks like this is causing problems. Interesting. Probably because we already did that somewhere else and just didn't know. Alright, let's add a little bit more density. Yeah, looks like it's good now. I'm not sure really what happened there. Interesting. Looks a little choppy, eh? Let's add some absorption. Okay, so it looks like this wasn't the problem. Okay. Interesting. Alright, so that's a bit curious. Maybe it's this that's causing the issue. Well, that shouldn't be happening. Okay. Okay, so let's think about this logically. So we have our absorption color, we're getting the red of it. Let's change our absorption amount to 0. Let's first see if this does. Okay. So set this to 0, let's figure out what's going on. So theoretically, so maybe if we multiply this by -1, and add 1, that's it. That's what it was. I forgot about that. Okay. multiply by -1. There we go. This should be better. Wait, what's going on now? It should be the same. Multiply by -1. Okay. Then add 1. Jeez, man, what's going on here? Oh, yes. Forgot to do this. And then this. Yep. Perfect. Alright. Now let's add some absorption in. Let's make sure that this works as well. Let's change our color to something a bit more reddish. What if you add more absorption? Nice. Let's change the density. So we aren't getting a whole lot of stuff right now, right? I mean, we didn't really expect a whole lot of it. So you can see, yeah, we get much more. So, I mean, this technically works as an atmosphere, but it's not fully functional because, I mean, we don't even have capability to change the light color or the light position, and therefore through that get sunrises and sunsets, and that's what we're going to be doing next time. That's going to be where a bit of an iterative function comes in, because doing light computations while going through an atmosphere is still quite difficult. This sort of integration, I'm going to be playing with putting that into the same integration function, but I am not expecting to get a whole lot of good results from that. So yeah, I'll see you guys when that tutorial drops. For now, have a good one, and let's see how many views this can get. By the way, this is so heavy in math, I highly doubt that I'll get any views, but I will be pleasantly surprised. So have a good one, guys. I'll see you later.